It's good to begin by saying that there are three main factors that decide if a part will print to specifications: design, materials, and printing process. The accuracy of a printed part depends heavily on its design. If your design isn't optimized, variations in cooling and curing can result in internal stresses. This can lead to warping or shrinkage. 3D printing, in general, is not suitable for flat surfaces or long, thin, unsupported features. Also, dimensional accuracy will decrease as part sizes become larger. Specific design recommendations for each of the technologies can be found in our knowledge base. You'll find the links below. Like design, dimensional accuracy also depends on the material being used. What we see often at hubs is that an engineer we work with wants to sacrifice the accuracy of a part for the enhancement of a specific material property. For example, a standard SLA resin will produce more dimensionally accurate parts than flexible resin. For parts where high accuracy is critical, standard printing materials are recommended. Moving on to discussing the different printing processes. Let's start with FDM. Fused Deposition Modelling, or FDM, produces parts one layer at a time by extruding a thermoplastic onto a build plate. This can cause problems for large parts as it creates temperature variations across the build platform. As different areas of the part cool at different rates, internal stress causes the print to deform. This can lead to warping or shrinkage. Solutions like printing rafts, heated beds, and radii at sharp edges and corners can help to reduce this. Thermoplastics that require a higher print temperature are more at risk. Adding a radius on the bottom edge in contact with the build plate or a brim is recommended. Shrinkage usually occurs in the 0.2 to 1% range, depending on the material. Note that different materials are more prone to warping than others. For example, ABS is known to be more susceptible to warping than PLA. If you have overhangs over 45 degrees, you will most certainly need support structures to create accurate parts. Next, SLA. SLA, or stereolithography printers, use a laser to UV cure specific areas of a resin tank to form a solid part one cross-section at a time. These cured areas, however, are not at full strength until post-processing with UV. If a part is not properly supported, it generally doesn't print. Dimensional discrepancies can also occur because of the peeling process used by some SLA printers. The pulling force during the peeling process can cause the soft print to bend, which can accumulate as each layer is built up. Third, SLS. Selective laser sintering, or SLS, produces parts with high accuracy and can print designs with complex geometries. With SLS, a laser selectively sinters powder one layer at a time to form a solid part. To restrict the likelihood of shrinkage or warping during printing, SLS printers use heated build chambers. The powder is heated up to just below sintering temperature. However, this still results in temperature gradients in large SLS parts. This happens as the bottom layers of the part have cooled, while the recently printed top layers are at a higher temperature. Shrinkage usually occurs in the 2 to 3% range. To further prevent warping, parts are left in the powder to cool slowly. Support structures are not required for SLS, as the powder in the build chamber provides this. Moving on to material jetting. Material jetting is considered the most accurate form of 3D printing. Because there is no heat involved in the printing process, warping and shrinkage rarely occur. Most dimensional accuracy issues are related to features and thin walls that are printed below printer specifications. In material jetting, support structures are required to print overhanging or bridge features. The support is a solid structure taken from a soft secondary material that is removed after printing. The solid nature of the support results in surfaces that, coming in contact with the support, are being printed to a high level of accuracy. Care must be taken when handling parts produced via material jetting. They can warp and dimensionally change as a result of exposure to ambient heat, humidity, or sunlight. Finally, metal 3D printing. Metal printing, specifically DMLS and SLM, use a laser to selectively sinter or melt metal powder to produce metal parts. Much like SLS, metal printing produces parts one layer at a time in a controlled, heated environment on industrial-sized machines. As mentioned before, the layer-by-layer construction, coupled with the high temperatures involved in the process, create thermal differences. The subsequent effect is that stresses are built into the part. As a result, metal printed parts are at high risk of distorting or warping, meaning good design practices and part orientation are critical to achieving an accurate part. Bracing and support are used to help reduce the likelihood of this occurring. Unlike SLS, support structures are vital to minimize the distortion of the part during production. Parts are also generally built upon a solid metal plate and need to be removed once the print process is complete. Solid and lattice support structures are needed to help keep the part securely attached to the print bed. Most parts are also stress relieved via heat treatment process after they've been built and before being removed from the build plate. Doing so allows the crystalline structure to relax, preventing failure later. To finish this video, let's discuss some rules of thumb. For the highest accuracy and when budget is not a constraint, material jetting is the optimal solution. For high accuracy, SLA is recommended for parts smaller than 1,000 centimeters cubed, and SLS for parts with dimensions greater than 1,000 centimeters cubed. For quick, cost-effective prototyping, FDM is the best solution. That's it for this video on dimensional accuracy for 3D printed parts. I hope you learned something. Drop any questions in the comments below, and don't forget to like and subscribe. See you in the next video.